Welcome to the second implementation list lecture. We're going to be talking about linked list implementation of the list interface. So let's review the list interface. As you recall, list extends collection and provides methods to get an item at a particular index of the list, set the item at the particular index of the list, search for an object in the list, returning the index that the object is at, or -1 if the object's not in the list. We can remove an item from the list by calling remove, and we remove at a particular index. We can find the size of the list, how big is the list. We can add an element to the end of the list by just calling add, and we can add an element anywhere in the list by calling add with an index. We'll insert the element at that index and shift all the list items further down. Any ones with the index greater than that will be shifted down. So the linked list class, which implements lists, uses nodes to store data instead of an array. Now what this means is there's no wasted space. We don't have that extra space that's at the end of the array that is not being used, so we don't have that wasted space. We don't have to copy elements when we do an add in the middle, because each node knows who's next in the list, and so they just have a pointer to the next node, so we don't have to copy. We can insert a node in between by adjusting the next pointers. One problem is that the linked list only knows the start of the list, and so in order to get, we have to traverse the list to the index to get the item or set the item. Also, because the linked list only remembers the head, it's more complicated implementation than the array list. We have to have some helper methods to help us implement the linked list. So the first thing is we need to have a node that is storing the data in our linked list. So we have a private static class node. It's private, so it's only visible to the linked list class. You cannot return a node to the outside world because it's private. The node has a private data of type E and a reference to the next node in the list. So here's a graphical representation. We have the node, we have the data we're storing, and we have the pointer to the next node in the list. Now if that next pointer is null, that means that this node is at the end of the list. Now we need two ways to create the node. So we have a simple single parameter constructor that we set the data item to the parameter. We set next to null. We have a 2-parameter constructor where we supply the data item and the next node for this node. We assign the data item to data and we set next to the next reference. And that's it. That's the node class. There's no getters, there's no setters, there's no toString, there's nothing. It's a very simple class. And the linked list can access the private data and the private next because they're private inside of the linked list class. So all the member variables of the linked list class is we have a node head, which is a member variable that points to the beginning of the list, and the size of the list. We have to remember the size. We don't want to have to keep counting the size of the list every time someone says how big the list is. If we just remember it, then we can save a lot of time. We'll save a traversal and make the size method very quick. But in order to implement this class, we need some helper methods to help us out, because we're going to be doing a lot of this stuff along the way. The first helper method is addFirst, so we want to add the entry to the beginning of the list. So what do? We create a new node with the entry, and its next points to whatever head points to. So we create a new node with its entry, and its next points to what head was pointing to. We then assign head to this node. So now we've inserted a new node that points to whatever head was pointing to. So now we have to increment the size because we added one item to the list. And we're done. We've added a new item to the beginning of the list. The next helper method is to add after a node. We're going to add the entry after the node. Very similar to addFirst. We create a new node with the entry, and its next is whatever the node's next is pointing to. So we have the entry, the next pointer is pointing to what node's next was, and now we have to point node next to it, thus inserting this new node into the list. And because we inserted the new node into the list, we increment its size. We didn't have to shift anything in the linked list. They are all in the same order as they were, except for this new node is inserted after the node we were given. We want to have the flip side of those adds. We want to have helper methods to remove. So we want to remove the node after this node. So the first thing is we create a temp pointer to the node we want to remove, because we don't want to lose it when we move the next pointer. So we then change node next to point to temp next. So we say node, change node next to point to temp next. And now this node is no longer in the list, because the next node for this is over here and not here. We decrement the size because we removed an item from the list, and we return the old data that was removed, the data that was removed from the list, which is the data. If temp is null, which means node is at the end of the list, we're done because you can't remove anything after the end, at the end of the list, so we return null. We want to we want to remove the first item from the list. Again, we create a temp equals head, so we point temp at head because we're going to remove this item. If head's not null, we then move head to head.next. So now we've just skipped over the first node in the list. Then if temp is not null, there's something there that we skipped over. We decrement the size and return temp.data. Now if temp is null, which means head was null, then the list is empty and we can't remove anything, so we return null. The last helper method is the getNode, which traverses the list and returns the node at the given index, or null if index is greater than the size of the list. So what do? We set up a node that points to the head, and then we loop until we get to index, or we've gone off the end and node is null. So if the index is 0, we're there, we return node. If index is 1, we do the loop once, we're now here. We then, if we're done, if index is 1, we would then return this node. If it's 2, we would return this node. If it's the size of the array, we would return this node. But if index is greater than size, node would move to next, which is null. The loop stops, we return null, just indicating that we've fallen off the end of the list. So now that we have the helper methods out of the way, let's start implementing the public methods of the linked list. We have a default constructor that creates an empty list. We set the head to null, which means it's empty. The head is the end, and we set its size to 0. Very simple. The next method is add at the index an entry. We check the size of we check the index to make sure it's within a valid index. We can't add at negative, and we can't add beyond the end of the array, or excuse me, out of the end of the list. You can only add in the things. If it's out of bounds, we throw an index out of bounds exception and give the index that it's your bad answer. So now, if the index is 0, that means we want to add it first. We call our helper method addFirst, given the entry. The size will be incremented. We've added to the head. Else, we want to traverse the list until we get to the one before where we want to insert the node. And so we do an add after the node that is one before the index and the entry. So we've added a new node, add index, and we've incremented the size, and we're done. Add means add at the end. We simply call the add, and we provide the index of size, the entry, and we return true. get method, again, we check to see if the index is valid. Again, this time note that we changed the greater than to greater than or equal, because you can't get something at size because we're a zero-based list. If it is outside the bounds, we throw an index out of bounds exception, and then we traverse to the node at the index, and we return its data. Again, we're not returning the node, we're returning the data at the node, because the node is private and you can't return a private class, an instance of a private class to the outside world. The set method, very similar. Check the index, traverse to the node, remember the old value at the node, set the node to the new value, and then return the old value. Remove, we simply check the bounds again. If it's 0, we remove first, else we go one before, and we do removeAfter. Very similar to the add method. So what are the big O comparisons between our array list implementation and our linked list? Big difference right here is the get method in an array is very quick because we just grab the item in the thing. In our linked list, we must traverse the list to get to the index, so that's why it's big O of n. Index of, you just got to search the list. You got to search the list. You go from the beginning to the end. You have to do a search, big O of n. Remove, again, for the array list, we had to copy all the items over to fill the gap. In the linked list, we had to traverse to the location, but we didn't have to do the copy. The traverse is big O of n. The copying of the data is big O of n. Size, both implementations remember the size of the list, so that's big O1. Add, again, if you add and the array size is too small, you have to do a copy, which is the big O of n. In the add, at the end, we had to do the traversal, that's the big O of n. Added index, we have to do the shifting, that's the big O of n. And here we had to do the traversal, so that's big O of n. Thank you very much.